Hello friends, good morning. I welcome you all for today's session. So in today's session we'll be dealing with the last problem on torsion of shafts. So this is a bit different from what we have solved in the previous two classes. Right, so here we are having a composite stepped bar or a stepped shaft as I shown in the figure. When I say composite, it is made up of two different materials. So he has given that one is made up of aluminium and second one is made up of steel. Torsion is acting at this particular point, right? Then he has asked us to find out the maximum stress in aluminium and steel shafts. So I need to find out the maximum stresses. If I want to find the maximum stresses, first I need to find the angle of twist. So without finding angle of twists, it is impossible to determine the stresses using FEA, right? So indirectly is asking us to find out both angle of twist as well as the shear stresses in both the materials. Right, now before we could proceed further, first we need to have a look at some important changes in unit which I'll be making. Now before that, you just go through this statement of the problem. He has given us the diagram and I have converted into the equivalent element diagram. So here this is element number 1, you are having element number 2, you are having element number 3. So we are having 3 elements. Right, length of the elements are known. Now here modulus of rigidity he has given in GPa, whereas your length is in mm. Also the diameters are in mm, right? So this is also in mm, this is also in mm. So I need to convert this GPa into mm, right? So that conversion is important. So that is what I have done here. And we'll just go through that, then we'll start with the problem. Okay, G of steel as given in the problem is 84 GPa. GPa is gigapascals, which is 10 raised to 9. So it is 10 raised to 9 pascals. So 1 pascal is equal to 1 Newton per meter square. So 84 into 10 raised to 9, it becomes Newton per meter square. Next, you know that 1 meter is 1000 mm. So 1000 mm, we are having square, the square you keep it as it is. So 84 into 10 raised to 9. So 1000 square, it becomes 10 raised to 6 mm, the whole square becomes mm square. So now it is Newton per mm square. 10 raised to 6 and 10 raised to 9, the outcome will be 10 raised to 3. So when you convert 84 GPa into Newton per mm square, it is 84 into 10 raised to 3 Newton per mm square. Very important from your exam point of view. If you are going to directly substitute as 84, then your answers will be wrong. The entire problem will be wrong. So be careful. First check out the units given in the problem, compare it with other units. Units should be uniform throughout the problem, right? Similarly, GAL, that is modulus of rigidity or torsional rigidity for aluminium, is given as 28 GPa. It will be 28 into 10 raised to 3 Newton per mm square. Fine. So next we'll be starting with the problem. Now before I could start with the problem, let me calculate the polar moment of inertias. So it is given by pi d raised to 4 divided by 32. Okay, there are 3 elements, so I will be having 3 polar moment of inertias. Element number 1, element number 2 and element number 3. So for element number 1 and 2, which is made up of same material, that is aluminium, let me check out what it comes out to be pi, and the diameter of aluminium section as given in the problem is 50 mm, right? So it is 50 raised to 4 divided by 32. So J1 is equal to J2 is equal to, it comes out to be 613.59 into 10 raised to 3. Unit will be mm raised to 4. Okay, now similarly J3 will be pi d raised to 4 divided by 32. Now the value of d is going to change because now it is the steel shaft. The diameter of the steel section is 25 raised to 4 divided by 32. So it is approximately 38.349 into 10 raised to 3 mm raised to 4, right? So these are the prerequisites which are required before I could start with the problem. If you are done with this, then we'll be starting with first step of the problem. So you already know what is the first step of the problem. So first step is find elemental stiffness matrix. Find elemental stiffness matrix. Okay, elemental stiffness matrix formula you know, K1 is equal to G of aluminium into J1 divided by L1, 1 minus 1 minus 1 1. So it comes out to be G of aluminium is 28 into 10 raised to 3, 10 raised to 3. J1 I calculated as 613.59 into 10 raised to 3. Length of first element is 200, right? 200. These are keep it as it is, 1 minus 1 minus 1 1. So if you simplify, K1 comes out to be 10 raised to 6, 85.9 minus 85.9 minus 85.9 and 85.9. Please note down the associated angle of twists: theta 1, theta 2, theta 1, theta 2. Right? How you are going to decide it's theta 1 and theta 2? Consider element number 1. So this is element number 1. The two extreme nodes are 1 and 2, so it is theta 1 and theta 2. Now, similarly, if you calculate K2, you will be getting K2 value as 171.8 minus 171.8, 171.8 with a negative sign and 171.8. Associated nodes are theta 2, theta 3, theta 2 and theta 3. Right? Fine. Theta 2, theta 3, theta 2, theta 3. Now thereafter we need to go for K3. Now K3 you should be careful, because here there will be change in modulus of rigidity. These two elements were for aluminium. In the second thing only the length is going to change. In the first case it was 200, in the second case you need to take the length as 100. Now here the formula will be steel into J3 divided by L3. So it is 1. We are getting it as 1 minus 1 minus 1 1. Now G for steel comes out to be 84 into 10 raised to 3. J3 value is 38.349 into 10 raised to 3. I already calculated it, so I am taking it directly. You can refer the calculation, you will get to know how I have done that. L3, length of element number 3 is 300. It is 300, right? Here I have calculated J3, it is 38.349 into 10 raised to 3. So I am utilizing these two things. So here it is 300, 1 minus 1 minus 1 and 1. If you simplify and resolve this, you will be getting the value of K3 as 10 raised to 6, 10.73 minus 10.73 minus 10.73 and 10.73. Once again, please don't forget to write the associated nodes. It is very important, right? So it is theta 3, theta 4, theta 3 and theta 4. So this will be the first step, which is calculation of elemental stiffness matrix. Next we'll be going for step number 2. We'll be going for step number 2. So step 2 is find global stiffness matrix, right? I need to find out k such that it is sum of k1, k2 and k3. So if I do that, the global stiffness matrix comes out to be, I just need to merge everything, so it comes out to be 85.9 minus 85.9, 0 and 0, minus 85.9, 257.7, minus 171.8, 0. These two elements will be 0, minus 171.8. Next you are having 182.53 minus 10.73. This is 0, minus 10.73 and 10.73. Right, so this is 10.73. Right, so be careful because it is a 4 into 4 matrix, so that is where your theta 1, theta 2, theta 3 and theta 4 comes in handy. Right, it helps you to formulate this correctly. Okay, so that is your global stiffness matrix. Next we go for FEM formulation, that is third step. From FEM formulation, you are having k into theta matrix is equal to T. K I am having it, I will copy it as it is, 10 raised to 6. So 85.9 minus 85.9, 0 and 0, minus 85.9, 257.7, minus 171.8, 0, 0, minus 171.8, 182.53, minus 10.73, 0, 0, minus 10.73 and 10.73. Right, so that is my global stiffness matrix. Angle of twists theta 1, theta 2, theta 3, theta 4. Now I need to write the torques, be careful. Now let me refer to the element diagram for T1, T2, T3 and T4. Let us check out. Now if you refer this diagram or this diagram, whichever diagram you may refer, it is fine, because this element diagram is constructed from the diagram which is given in the problem. So there is only one torque which is acting, that is at node number 2. So T1, T3 and T4 are by default 0, and here it is 200 into 10 raised to 3 because it is in Newton meters and all the units which I am using here are in mm, so this meter should be converted into mm. So at point 2, it is 200 into 10 raised to 3, and for all remaining things it becomes 0. Now by applying boundary conditions and using elimination approach, right, we get, so if you are applying boundary conditions, we need to put theta 1 is equal to theta 4 is equal to 0. Right, we need to put theta 1 is equal to theta 4 is equal to 0. Why? Reason being simple, because theta 1 and theta 4 are the extreme nodes where the angle of twists will be 0 because both the ends are fixed. So in that case, when theta 1 is 0, I need to strike out the first row and first column, and theta 4 is 0, I need to strike out the fourth row and fourth column. So remaining, if I just multiply, I'll be getting it as 257.7 into theta 2 minus 171.8 into theta 3 is equal to 200 into 10 raised to 3 minus 3. How minus 3? Here I am having 200 into 10 raised to 3, but also you are having 10 raised to 6. So if 10 raised to 3 is divided by 10 raised to 6, because if I take this 10 raised to 6 on the right hand side, it goes into the denominator. So 10 raised to 3 divided by 10 raised to 6 comes out to be 10 raised to minus 3. Now second one, minus 171.8 into theta 2 plus 182.53 into theta 3, it comes out to be 0. Right, so you are having two equations and you are having two unknowns. So if you solve this solving, so what we'll be getting here is theta 2 will be equal to 2.0833 into 10 raised to minus 3, and theta 3 will be 1.9608 into 10 raised to minus 3. Both will be in radians. This is important. Okay, so once if you calculate these associated angle of twists, now you can easily calculate the maximum shear stresses in both the materials. Right, so the last step is step number 4, calculation of shear stress. So in the first case, tau 1, which is made up of aluminium, so in that case it is G aluminium into R1 divided by L1 minus 1 theta 1 into theta 2. This is the formula which I'll be using, right? Because the first particular element which I have taken in the problem is of aluminium. So G for aluminium is 28 into 10 raised to 3. R should be taken as 25. Why? Because R is radius and the diameter given in the problem is 50 mm. So half of 50 is 25. Length of the first element is 200. So minus 1 as it is. Right. Next, theta 1 is 0. Theta 2 is 2.0833 into 10 raised to minus 3. Right, so this is 2.0833 into 10 raised to minus 3. So if you just resolve this, multiply with this matrix, then if you multiply with this, I'll be getting the value of tau 1, which is made up of aluminium, as 7.29 Newton per mm square. So that is stress in the first element. Right, now similarly, stress for the second element, which is also made up of aluminium. Okay, the everything is going to remain same. I'll tell you what are the changes being made. GAL will remain same, R1 will remain same, L1 becomes L2, so it is minus 1 and 1. So for second element, associated nodes will change. It will be theta 2 and theta 3. Right, so here it will be 28 into 10 raised to 3 into 25. Length of the element is 100. So minus 1 and 1. Theta 2 and theta 3 values, I've got it, 2.0833 into 10 raised to minus 3. Right, that is the value of theta 2. Theta 3 is 1.9608 into 10 raised to minus 3. Okay, you are well acquainted with multiplication. You solve this entire thing, you need to multiply with this matrix, and the outcome of this matrix is to be multiplied with this matrix. Right, if you do that, you'll be getting the stress as minus 0.857 Newton per mm square. Right, so that is stress in the second element. Now at last we'll go for stress in the third element. Okay, so stress here in element number 3, tau steel should be equal to tau 3. Okay, it is important tau steel because it is made up of steel material, so it is G of steel into R3 divided by L3 minus 1 and 1, associated are theta 3 and theta 4. Right, so this is the formula. So tau steel is equal to tau 3 comes out to be 84 into 10 raised to 3. Now R is 12.5 because radius is half of diameter, and diameter given in the problem is 25. L is 300, so it is minus 1 and 1. Theta 3 value is 1.9608 into 10 raised to minus 3. Theta 4 is 0. Right, so if you resolve this, we will be getting tau of steel as 40.88 Newton per mm square. Right, so that is the end of the problem. He has asked us to calculate the shear stresses, so we have calculated it in aluminum material as well as steel. To calculate that, first we need to know the angle of twists, and that is what we have done. Right, now before winding up today's session, as usual we'll be seeing few force terms which will be helpful for us in our competitive examinations, and which each and every one of us should do as a part of FEM. Right, so it is very important to know these terms. Right, so the terms I have listed here, I call them as force terms, and in that I have resolved this force, or I have divided this force into two types: internal forces and external forces. So whenever I say external forces, these will be acting upon the body or on the body, and internal forces are the reactive forces which are generated in the body as a result of application of external force. In short, reactive forces are nothing but stresses which are inside the body, and external forces are acting outside the body, external to the body. Now external forces can be of three types, right, which are those. First one is body force. So body force is denoted by, or it is designated by, small f. It always acts on an elemental volume, right? It always acts on an elemental volume, and that is the reason you can note its unit is Newton per meter cube. Example can be self weight due to gravity and inertia force. Right, now this self weight is written in mechanics as rho into g. Now unit of rho is kg per meter cube. G is acceleration due to gravity, meters per second square. Now if you just club these two things, kg per meter cube into meter per second square, it is mass into acceleration, F is equal to m into a, which is Newton. Right, so Newton per meter cube. So rho into g is nothing but self weight due to gravity. Next comes inertia force. Inertia force also comes under body force, which will be acting on an elemental volume. The second type of force which we need to know about is traction force, denoted by or designated by T. Unit will be Newton per meter square. An example of that would be viscous drag. That is, if there are two layers of fluids which are flowing one over the other, right, the in between drag, or the resistance between these two layers, I call it as viscous drag, right, because the entire surface area of one layer will be acting as a resistance for the layer above that which is moving on that. Right, so viscous drag is nothing but the drag force in between two fluid layers. I call that as viscous drag. So if it is a solid part, then it becomes surface shear. If there are two surfaces which are in contact with each other, which are rubbing with each other, then it becomes surface shear. If it is a fluid one, then it becomes viscous drag. And at last it is point load, which is the very normal force what we apply, so it is denoted as N. This point load is generally known as concentrated load, and it acts at one point only, right? It acts at one point only. Its unit is Newton. So these are the important types of forces which we need to know. Remember, body force is denoted by F. Its unit is Newton per meter cube because it acts on an elemental volume. It acts on an area, that is the reason its unit is Newton per meter square, and it is acting at one single point, so it is Newton, right? So that's it for today's session. Thank you. Please do subscribe my channel, and also keep updated with the syllabus, because in the next class we are going to start up with a new module. So go through these videos. If you are having any doubts, please do ping me in my personal window, or you can put it in your comment section. Thank you. Have a good day.